So
Yeah. Yeah, so depending on the axial planes, we have these classifications. With vertical or near vertical axial planes, we call them upright fold. If the axial plane is more or less horizontal or dipping at a very low angle, for 10 degree, we call them recumbent fold. So if the axial plane is inclined, then we call them, so more than 10 degree, we call them inclined fold. And if an axial plane, it's, this is a bit tricky, if a fold, so more or less if a fold is like this or this, we call them reclined fold. So how is that possible? Suppose you have an inclined fold which has the axial plane, which is a pitch of the fold axis on that axial plane is between, so the fold will be somewhat, say for example, um, the fold axis, can I show you one picture of the fold axis, is like that. So it will be something like that. So the pitch of the fold axis, which is this one, will be around 90 degrees. So 80 to 100, this is the definition. So up from 80 to 100, we will get, if we have this thing, then we will call them inclined fold, right? Is this clear? So upright, we have a vertical horizon, vertical axial plane. Recumbent, we have, so recumbent is more or like neutral fold, right? And then we have inclined fold, we have reclined fold, and we have overturned fold. When you have both of these limbs are dipping in the same direction, right? This is clear.
yes, sir.
And depending on the fold axis also, we can classify the folds. So this is when the fold axis is horizontal, we call them horizontal fold. When the fold axis is plunging, we call them plunging fold. And we have, just one second. Hello? Yeah, are you there?
Yes, sir. Camera off हो गया था आपका सर.
Yeah, yeah. Yeah, so depending on the fold axis, we have this horizontal fold, this plunging fold, and vertical fold. So yeah, coming back to the again the definition of fold axis. So in the definition, I said that if you translate the fold axis, you will end up with a fold, but that is not always true. You will end up with a cylindrical fold. In case of cylindrical fold, this the definition applies. So if you translate the fold axis, the fold you are generating, that will be a cylindrical fold. In case of non-cylindrical fold, you won't have an uniform fold axis. You have a fold axis here. If you measure the fold axis, it will be plunging, inside the screen. And if you have the fold axis measure the fold axis here, the fold axis will be plunging outward the screen, right? And here if you measure the fold axis, it is always varying, right? So it is like here the fold axis is oriented outward the screen, here also outward, and here it is more or less parallel to the screen, right? So these are the non-cylindrical folds on the basis of um, fold axis. This is the curvature of the fold axis. But there is a difference between these two and this one. What is that? Like in these two, for these two folds, the axial plane is planar, and this case also the axial plane is planar. Even though the fold axis are different, in this case the axial plane is a the axial plane is planar, right? But here the axial plane is carved. So axial surface we can call them, so it's carved, right? It's not one single axial plane. So yeah, so for these two cases we call them planar. This is planar cylindrical fold. This is planar or plane non-cylindrical fold. This is non-plane non-cylindrical fold, and this one is non-plane cylindrical fold. Why this is cylindrical? Because the fold axis is constant. If you take one fold axis here, if you translate that in some way or something like that, in this way, if you translate this thing, you will end up producing this fold, which is non-plane cylindrical fold. Okay. Yeah, so depending, as I said, that depending on the interlimb, why do we measure the interlimb angles? Because to classify these folds, right? So if you have a gentle fold, so the interlimb angle will be 180 degree to 120 degree. If this is an open fold where you have 120 degree to 70 degree interlimb angle, and this is closed fold where you have the interlimb angle between 70 degree to 30 degree, and here is tight fold, and here is isoclinal fold, right? So in isoclinal fold, the two limbs of the fold, they are more or less dipping towards the same direction, right? So they have the equal dip and equal direction. So isoclinal fold, it's almost like this, right? And so you have very tight hinge, and it's like this, almost like this, right? And there is another fold which called them fan fold. These are very rare, but here so here we have two hinges. So this is one hinge, this is another hinge. We have two hinges, and what is negative interlimb angle means it is carved inward like this, right? So then we call them fan fold. So these are very rare. So yeah, so depending on the shape of the hinge, we may also differentiate folds. So this is king fold, and we have sharp change of limbs, very sharp change, then we call them king fold. In chevron fold, you basically get, instead of this sinuous pattern, you get lots of V's, right? Then we call them chevron fold. So in consecutive folds is like it has a very, it doesn't have, basically consecutive fold doesn't have a limb portion. So this is a hinge portion, then another hinge portion, then another hinge portion, like that. And box fold is more like this fan fold, as I just said, right? So it has two axial trays, two hinges, like those things, right? Yeah. So, and there is a harmonic and disharmonic fold. So harmonic folds are those folds, suppose this is the thickest fold right here, and the fold that is following the wavelength and amplitude more or less following, just suppose this dark green fold. However, if it is thinner than this one, but it is more or less following this fold, then we call them harmonic fold. But if it doesn't follow, like for this fold and this fold and this fold maybe to some extent, then we call them disharmonic folds, right? So what is so how do you identify the disharmonic fold and how the harmonic fold in the field? So in case of harmonic fold, you can get one single trace of axial plane, right? So suppose the folds are following one another, so if you will get the same axial plane for all the folds. But here you will see, like, this is one axial plane, but it doesn't have axial plane here. So it's somewhat if for this section, if you consider this is, there is no axial plane. For the here this is axial plane, but here is no axial plane, there is no change, right? So these are called disharmonic folds, right? Yeah. So as I was telling, the S1, S fold and Z fold, so we always have to consider the long, short, and then long convention. So here, if you consider this one, so if you consider just short, long, and then short, then it will be S instead of Z, right? Suraj, Suraj, are you there?
Yes, sir.
So you see here, if we follow the short, long, and short convention, then this will turn up to be S, right?
तो हमको एक ही कन्वेंशन लेके चलना होगा, और जहाँ तक मुझे लगता है लॉन्ग
That,
शॉर्ट लॉन्ग ही है.
ha, that's what I meant. Okay. Yeah, so and periodic fold and non-periodic fold is more like the function that we use. Like, so periodic function means that it repeats after a particular interval, right? So this case with the periodic fold and non-periodic fold, when we have this equal wavelength.
Sir, you are not audible.
I am not audible. Hello, am I audible?
Yes, sir, you are audible.
Okay, yeah. So in case of periodic fold, you have the same wavelength, right? But here the wavelength differs. Like here is this much, and here is this much. And here. So it differs, right? So non-periodic fold means, so the fold, the hinges, the crest and the trough, they are not equidistantly spaced, right? Equispaced, right? Here they are equispaced. So this crest, so distance between this crest and this crest is equal to the distance between this crest and this crest, right? So in case of, and so is the with troughs, right? So here the this distance is more or less equal to this one. In case of this fold, like this is very short than this one, right? And this is the, and the amplitude also differs, right? So yeah. So a-national folds is a different kind of folds where you just so if you just move for a strike slip fault, you may say strike slip transverse fault, transverse fault, yes. But strike slip transverse fault, you may end up with this a-national folds. So a-national forms for folds are, they are also very rare. So it looks somewhat like this, small bumps or humps. They are arranged in arrays, repeated after some for some distances like this. Yeah, and there is defilement surface. So if there is a sharp competency contrast, say for example this one, this dark brown layer is not as much ductile as this layer. So what will happen, this layer will flow, and will this layer, the orange layer, is form fold, but this cannot form the fold. So what it will happen, it will be kinked and there will be some falls, right? And there will be some detachment from the surface. So here is the compression is coming from this direction and this direction maybe. So it will just pile up on the top of that. It's just like, suppose in a bed sheet, if you just move the bed sheet to, if some kind of folds appear, right, and it gets detached from the bed, right? So the same things happen in these cases, right? Okay. The interfolial fold, they are also rare. So in the shear zone also you can get this. So when the layer is extremely ductile, so in that case you may get a fold which is trapped in between the foliations, right? So very ductile folds. And that, for that we need very high temperature also, because to bend a rock in this, or a mineral, say for example maybe quartz, or it can have a phyllosilicates also. Mostly it will be quartz, because phyllosilicates, it will produce kinks. And so it is very rare, but with high temperature and very large deformation, which is only possible in the shear zone, you will get this kind of interfolial folds. Okay, so anything from this lecture? Anyone? I don't think so. Moving on. So in this part we will be doing some kind of mathematical classification. Like Ramsey, he classified the fold on the basis of deep isogons. So what is a deep isogon? So suppose you have a fold like that, and if you connect the points which have the same dip, right? If you connect like this point and this point, they have the more or less same deep. So if you connect these two planes, these 2 points, the line connecting those 2 points will be termed as deep isogons. All right. And if you draw tangent at those 2 points, as the depths of those two points are same, so these tangents will be parallel, right? So we will be getting one transverse thickness that will be termed as T alpha, and we can draw another capital T alpha which will be parallel to the axial surface trace. So this is a very uh, symmetric thing. Usually we, for asymmetric folds, these kind of calculations are difficult, but when you get asymmetric fold, you might get one symmetric fold somewhere. So more or less this doesn't really depend on symmetry, but this angle won't be 90 degree in case of asymmetric fold, right? So mostly if we consider the symmetric fold, what happens is that if so d5 isogons, they can converge towards the core like this one, or they can be parallel, or they can diverge, right? So what is the difference between these two? Here the spacing of the deep isogons is very less inside, and here it is larger than this one, right? So spacing is bigger here outside, so always in these cases. So these three cases where the deep isogon is converging inward, we will call them class 1 fold. If the deep isogons are parallel, we call them class 2 folds. If the deep isogons are diverging towards the center, towards the core, we will call them class 3 folds, right? But in case of class 1 class 1 folds, we can have 3 different subtypes, right? When the hinge thickness is minimum, the thickness of the hinge is minimum throughout the fold, and the limbs are thicker than the hinge, we call them class 1A. If the thickness is equal throughout the fold, we call them class 1B, or parallel fold. When the hinge thickness is maximum and the limbs are thinner, then we call them class 1C fold, right? And this is called similar fold. And so mostly in these cases you can see that, so the curvature, the curvature of the extrados and the intrados is same in case of parallel fold. In all the class 1A, 1B and 1C folds, the inward curvature is higher than the outward curvature, right? But in case of class 3 fold, the outward curvature will be more than the inward curvature, right? Yeah. So any doubt from this thing?
यस सर, जो
Yeah.
डीप आइसोगोन का जो लेंथ है वो टी अल्फा के इक्वल होता है.
It's deep isoconcal length, I mean this one.
यस सर.
Yeah, this is not T alpha. So T alpha is this one, right? This is not T alpha. All right.
यस सर, जो पीपीटी में सर टी अल्फा को ही लिखा गया है डीप आइसोगोन.
Where is it written? Can you just show me?
यस सर, दिस
Okay. Yes. So actually, in this case, the figure that is drawn, that is shown in the PPT. So here in this case, the T alpha is defined to be the deep isogon, right? But if the fold is carved like this one, if the axial plane is little bit carved like this one, so if you just tilt the axial plane, what you will see? You will see that this T alpha is basically, so T alpha is basically axial trace thickness, right? So this is axial trace thickness. So this T alpha is this one, this axial trace thickness, T0. So here, these things are differently defined that I can see, right? So it is written that T alpha is the deep isogon. Yes. You can say that T alpha is the deep isogon. So there are different things, but mostly we follow the PPT here because these things actually are taken from Ramsey's
जो
book.
रैमजे का सर बुक है उनके बुक में सर मैंने देखा था, तो उसमें टी अल्फा अलग सर डिफाइन किया गया था और डिपाइसोगोन सर अलग ही एक टॉपिक उसमें डिफाइन किया गया था.
Yes, that is what I think too, because okay, so thank you for pointing that out. Maybe I will send another email to all the students that there is another error. So yeah, so you follow the Ramsey's book, right? So this is this is his classification. Or else I can do one thing, I can send this material, right? So I upload it in the OneDrive, or I can send another material. Okay, so mostly these things you don't have to worry that much, because mostly these classifications are based on how deep isogons are converging, right? So deep isogons are those lines which connects the points of intrados and extrados, the points which have equal deep, right? Okay, so fold can happen in mostly three mechanism. One is buckling, in which you just compress and then the material inside will get buckled, right? And another thing is flexural folding. In flexural folding, what happens? The layers, they slide one past each another, and the slide, and then this product produces. Suppose you have a deck of card here, and just mark one thickness, one part of the card, and then you just push in the middle, and then you will produce some kind of fold, right? So that is called flexural fold. And if you bend something, that kind of folding is called bending. And passive folding is not a real folding mechanism, where it gets folded due to deformation of the top and bottom layer, right? So yeah, depending on the buckling, you have different equations. So these are derived from Navier-Stokes equation, I guess. So these are things that if you want, I can supply material for these equations, but these you don't need, right? In the undergraduate level, we don't need these things, right? Yeah, so depending on the mu1, the viscosity, you get different kinds of wavelengths. It is shown here. And flexural slip and flexural. So as I said, if you just bend this thing, so there will be slip along this layers, right? So those are called flexural slip. This is same as the slip if you push the deck of cards. So all the cards will slip one past each another, and the centermost, the central portion of the deck will the slip will be maximum for the central part, right? And that's how the flexural folds form. And bending is just bending of the layer. If you so some point, it is mainly, it's not natural. In natural system you don't get this much. It's unlikely to get this kind of fold. So we mostly get buckle fold and flexural fold. Okay, and as I said, so yeah, see, forceful intrusion of soldomes, that can bend these things, right? And fault bend folds are not real folds, but yeah, these are some kind of folds that you can study. You will study. Okay, and the passive folding is, as I said, so it doesn't really receive any kind of any kind of forces. So the top part and the bottom part of the layer, it creates drag, and with that you get this kind of folding. Okay. Okay. So anything from this section? Any doubt?
No, sir.
Okay. Yes. So this part deals with the superposition of folds. So what happens in nature? You won't get a force that is coming from a particular direction. So it changes. So with time, if a force formed a fold, say north-south direction, and after some time, again another set of force it deformed the terrain from the east-west direction. So these two directions, when they converge, I mean these two deformation, when they converge, they create a superposition, right? So what happens in superposition? It just like the wave interference, that this wave superposition that we usually studied in physics. So in this case, suppose you have a deformation along this, like how I'm moving the cursor. If you have a deformation like this, and then you have again a force that is deforming the east-west direction, so it will produce this series of complex pattern, right? So there is so here we have multiple sets of forces, because if you trace the axial planes, it is radiating right from all possible directions. We have all the forces from all possible direction. So the safest idea to get the direction of the forces is from by noticing the axial planes. So if you have axial plane somewhat like in this orientation, you can all, it's safe to consider that the force came in these two directions, perpendicular to the axial plane, right? As we learned in the foliation part. So axial plane is one kind of foliation. Okay, so yeah, different types of superposition are there. So in case of type 0, as we studied, plane cylindrical fold, if you can remember those diagrams in the previous lecture, previous or the lecture just before that. So in type 1, the plane non-cylindrical fold, we call them type 1 superposition. Is non-plane non-cylindrical, we call them type 2, and type 3 is non-plane cylindrical fold. And these are different outcrop patterns that is very beautifully shown in this figure, in this lecture. See, these are different interference, and these are the different patterns that we will see in the field, right? So in the outcrop, you always, when you read, you go through this lecture, in the this you always notice these things, right? And you remember these things, because in the field we don't get this complete fold. Like some outcrop we will see, maybe some outcrop is cutting like this is one outcrop, maybe this is another outcrop, and this is another outcrop. So from that outcrop we have to figure out what kind of superposition took place, right? So if your superposition is, if its outcrop is at some angle, you will see this. So these are domes, right? These are domes, and these are basins, right? These are domes, these are basins. So you will see this circular thing, right? So and this the radius might get smaller here, the radius is huge. So it depends on how the outcrop, how the erosion took place. It depends on the outcrop, right? Yes, this is one field photograph. So you see, this is what we see in the field. We don't see the complete fold. So from that fold, so you see, so this is basically a basin, right? So it's dipping in this direction also, and it's also dipping in this two direction, right? But this, the axial plane that is parallel to this line, is the deformation is was more intense in this direction, so it compressed more, right? Yeah, see, this is how we see the field. This is all type 1 deformation. Okay, so this is an experiment. Okay, so in case of type 2 superposition, we get this hook or mushroom or crescent shape, right? Mushroom or like this crescent shape, right? Okay, so this is what we see in the field, the superposition patterns. Okay, this is another example. Okay, and this is type 3 superposition, where you get this kind of force, that is cylindrical but non-plane. So yeah, this is how you will see in the field, right? I'll show you some field photographs, then you will understand more. Okay, so like this one, right? Maybe this one also, right? Okay, so today we I don't think we can cover the next lecture because it's already 7:18. So I wish to continue today, but I am afraid that I cannot. So any question from this fault part?
No, sir.
Okay, anyone? If so, anyone else? Dilmurugan, I'm seeing you are unmuting yourself. You have anything to ask? Do you have anything to ask? Please respond. Okay, sir. M fold and W fold. Okay, yeah. So when you see that anticlinorium and synclinorium part, so the top part will be it's more or less similar to the letter M, so we call them M fold, and the bottom part near the uh, trough of the bigger fold, near that we call them W fold, because it's more or less similar to the word letter W, right? So W fold and M fold, that's there. It's shown in the PPT. If you go to the PPT and you go to the lecture also, yes, it's not, it's just terminology, right? So the top part we call them W, the bottom M, and the bottom part we call them W, right? Anything else? Okay, so if you do not have any question, then I am going to end the session. Is that all right? Yeah, thank you. Okay. Ram, you have anything to say? Okay, can't hear, but I think, okay. Okay, all right. Yeah, good night. I'll see you in the next class. Okay, so there is one more thing. I am guessing that you will be attending the next classes also. So, so the next week I'll be available. I'll be in my home, but I'll be available. So next day I'll be taking class. But the next to next day, I won't be available. I will be outside, right? I'll be attending some conference and I cannot take the class. So maybe we will have, I will send the mail, and maybe we will have another class, not on Monday, but some other day, right? No, next week there will be class. Next to next week, I won't be able to take the class, right? Okay, that's all right. That's all right. So the classes are on YouTube. So okay, so we will be taking those classes. Will I be able to complete the portion? Yes, you can. If you do, if you have any doubt, any, like, if you need any help, just drop a mail in the ask a question section, and I have another TA, and I, like, me and that person will help you to go through this thing. Okay, so don't worry, just drop a mail, right? So drop a mail in the ask a, yes, yeah, thank you, yeah. So drop a mail there, and that will be taken care of. Okay, yeah. So next to next we may have to reschedule the class, but till now we'll be having this thing. Okay, we'll be following the regular pattern. So next week there will be class. Okay, good night.